Hello and welcome to Adisha Tech Tutorial. So in this video we will be studying about the semiconductor part 2. So in the semiconductor part 2 we will study two types of current flow in semiconductor, that is drift current and diffusion current. So before studying drift current, let's see an animated video about the drift current. So here in this animated video you can see when we give no energy to the semiconductor, then what happens is the electrons moves randomly inside the semiconductor and they do not contribute to the flow of current. Now let's see what happens when we apply energy or we give electric field to the semiconductor. So in this animated video, you can see when we apply a battery across the semiconductor, electrons gain drift velocity and move in a particular direction, giving rise to the drift current. So now it is clear from the animated video that the drift current is due to the presence of electric field. So what is electric field? Electric field is formed due to the battery applied across the semiconductor. So by supplying battery across the semiconductor, what we will get? We will get a positive and a negative potential across the semiconductor, which will give rise to the electric field whose direction will be from positive to negative. So electric field direction will be from positive to negative. So this is a three-dimensional view of the semiconductor material. So electric field direction is from positive potential to negative potential of the battery. Now if this is the length of the semiconductor and V is the value of the potential difference across the semiconductor, and how we will be calculating electric field, then electric field E is represented by V divided by L. So if in question it is asked we need to find electric field, then we will calculate it by the given voltage divided by the length of the semiconductor. So now the current, that is the drift current, which we will calculate in terms of current density. Now what is current density? Current density is represented by J, which will be equal to the total current divided by the cross-sectional area of the silicon bar. So here this is the cross-sectional area of the silicon bar. So the total current crossing the cross-sectional area divided by this cross-sectional area will give us the current density. So here the drift current density is calculated as summation of the drift current due to the holes and the drift current due to the electrons. So let's calculate the JP drift, that is the drift current density due to the holes. So here you can see whenever there is electric field across the semiconductor, the current starts flowing, that is the movement of electrons and holes takes place. Now particularly how we can define the electric field? What electric field does is it is like a physical field that surrounds the electric charges and it also exerts force on the other charges. So what this electric field does is it exerts force on the other charges, means electrons and holes inside the semiconductor material. Because of this force, movement occurs inside the semiconductor and the electrons and holes moves with a velocity known as the drift velocity, that is V drift. And this V drift will be directly proportional to the electric field supplied. So V drift is directly proportional to electric field. If we equate it with V drift with E, we will substitute it with mu into E. So what is mu here? Mu is the mobility. Mobility of the electrons or holes. What is mobility? Mobility is the ease with which the charges move by the application of the electric field. So the velocity, that is the drift velocity, it is nothing but it is equal to mu times of E. So because of the holes, that is Vp drift velocity because of the holes is mu p into E. What is mu p? Mu p is the mobility of the holes. And what is Vn drift? It is the drift velocity due to the electrons, which is nothing but it is equal to minus of mu n into E. What is mu n? Mu n is the mobility of electrons. Now here you can see a negative sign, that is minus. Why this minus? Because electrons will move towards the positive potential, which is opposite to that of the electric field direction. So there is minus sign here. Okay. But why holes are positive? Because holes direction is same as that of the electric field direction. So we are getting plus of mu p into E. So now let's find out what is the drift velocity or what is the drift current density due to the holes. So in general we can write the current density J is equal to rho times of V drift or the velocity. What is the rho? Rho is the volume charge. Volume charge, what do we mean by volume charge? It is the value of the charge Q times the number of charges, that is the concentration of the charges. So it can be P or it can be Q. So Q times P or Q times it is N. Q times N times the drift velocity of which component we are finding, either electrons or holes. So now volume charge for your holes is equal to Q times of P. What is the value of Q? Q is equal to 1.6 into 10 to power minus of 19 coulombs. So Q times of P, P is the concentration of the holes times the velocity, that is Vp drift. So we can substitute Vp drift. Vp drift is mu p into E. So here Vp drift is mu p into E and the volume charge is Q times of P. So we got Jp drift, which is equal to Qp times of mu p into E. Let it be equation 1. So now let's find out what is Jn drift. So in a similar manner, we can find Jn drift is equal to rho v times of Vn drift. So here what is rho v? It is the volume charge of the electrons, which is equal to Q times of N. So it is Q times of N. N is the concentration of the electrons inside the semiconductor, and we will substitute the values of Vn drift, which is mu n into E. But in the previous section we have seen the value is minus of mu n into E. So where this minus has gone, the minus is has become plus because of the charge minus Q. Okay. So the charge of an electron is nothing but it is minus 1.6 into 10 to the power minus of 19 coulombs. Okay. So Q is 1.6 minus of 1.6. So the minus of the charge and the drift velocity is cancelled and we are getting Qn times of mu n into E. So we got our Jn drift is equal to Qn times of mu n into E. So now we can find the total drift current density, that is J drift, which is nothing but Jp drift plus Jn drift. So we will substitute the values of Jp drift. So this is equation 2. So substituting the value of equation 1 and equation 2 in our J drift total current density, what we will get? Qp times of mu p into E plus Qn times of mu n into E. So we can take Q common and we can find out in a simplified manner, that is P mu p plus N mu p times of E. Just take the Q common. So this is the important formula which we'll be using in our problem section. So this you got to remember. So now this value Q times of mu p plus N times of mu n is nothing but it is sigma. That is called the conductivity of the semiconductor. Okay. So the conductivity is nothing but it is Q times of P mu p plus N mu n times of electric field. Okay, so it can also be written as E divided by rho. What is rho? Rho is the resistivity, which is equal to 1 by sigma. Now what is resistivity? How it is related to resistance? So resistance R of a material will be equal to resistivity rho length of the material divided by the cross-sectional area of the material, that is A. So every material has different resistivity in it, and we can calculate the resistance of the material with the help of this formula. So how we can define rho? So here resistivity is defined as the ability of the material to resistance to resist the current. Okay, so this is the rho here. So we can now find an Ohm's law with respect to resistivity, electric field and current density. So here our Ohm's law, we can represent it as V proportional to I, or we can write it as V is equal to IR. So here your R will be equal to how much? V divided by I. So in comparison to with this formula, we can find an Ohm's law with current density, with electric field and resistivity. So resistivity here, it is compared with R. E is the electric field, which is compared with the voltage V, and J is the current density, which is compared to the total current inside the semiconductor. So this is the Ohm's law in relation with the semiconductors, and its unit can be calculated as ohm into cm, that is ohm cm. So this is all about your drift current density. Now next we will study what is your diffusion current. So now what is diffusion current? So we can study it with an example. So for an example, if we spray perfume at a corner of a room, after a certain time interval, you can smell the perfume all over the room. So what has happened? The smell of the perfume has traveled from the higher concentrated area, that is the corner of the room, to the lower concentration area, that is all over the room. So this is a property of nature, that always the particles move from a higher concentrated area to a lower concentrated area. So similarly, inside the semiconductor, the electrons or holes move from the higher concentration region to a lower concentration region. So in this figure, it is very much clear that the electrons present inside the semiconductor is moving from the higher concentration region to a lower concentration region, and after some interval you can see there is a uniform distribution of electrons inside the semiconductor. This is nothing but it is called the diffusion, and it is called the diffusion current inside the semiconductor. So now it is occurring without any external voltage given. So in case you can remember that in case of drift current, we are giving some external voltage and electric because of which electric field is formed and the electrons and holes are moving. But here in this diffusion current, no external voltage is required. Just the electrons or holes will be moving from a higher concentrated region to a lower concentrated region. So it is quite simple. So let's derive a formula for the diffusion current. So again, the diffusion current here, it is measured in terms of current density. So now for electrons, we will be finding the diffusion current density, that is Jn diffusion, which is proportional to dN by dx. Now what is dN by dx? dN by dx is called the concentration gradient. That is the difference in the concentration of electrons inside the semiconductor in a given area. So this can be measured with respect to the with the help of a graph. So this is the higher concentration region. So let the distance of the length of the semiconductor be x. So we can plot a graph of the concentration. So the vertical axis is representing the concentration of electrons, and the horizontal axis is representing the length of the semiconductor, that is x. So here you can see the electrons, here it is higher concentration. So at the initial level, so this is the initial level. So here the electron concentration is high, and slowly it is moving from the higher concentration to the lower concentration, and you can see we will get a graph that is exponentially decreasing. So this is nothing but represented by dN by dx, which is also called as the concentration gradient or the slope of the electron concentration. So here this slope is directly proportional to what? The diffusion current density, that is Jn diffusion. So in a real manner, what is moving? The charge is moving, that is Q is moving. And here you can see This is an exponentially decreasing curve. So here your dN by dx is negative. So your dN dx by negative, and the charge involved here is also negative for electrons. So the negative gets cancelled and you will be getting a positive q times dN by dx. So your Jn diffusion will be proportional to the charge times dN by dx, but it should be positive because of the cancellation of the negative symbols. Here one important thing you got to see is that the electron diffusion, okay, the electron diffusion is opposite to that of the electron current because of the conventional flow of current. The conventional current always moves in a direction opposite to that of the electrons. So now you are getting this, and we will equate it with a constant that is called diffusion constant, or it is also called as diffusivity of electrons. So your Jn diffusion is nothing but it is equal to dN q times dN by dx, where dN is the diffusion constant or diffusivity constant. So this is the equation for the diffusion current density due to the electrons, which we are forming with the help of the concentration gradient and the charge, and with diffusion constant, that is dN. So Jn diffusion is dN times q dN by dx. So this is the formula for Jn diffusion, that is the diffusion current density due to the electrons. Now moving on to the holes. So similarly, your holes will also move from a higher concentration region to a lower concentration region with respect to the length of the semiconductor. So here this curve is also decreasing exponentially. The slope of the curve will be negative, that is dP by dx. So here you can see your Jp diffusion, that is the diffusion current density, is proportional to minus of dP by dx, that is called the concentration gradient due to the holes. So here your Jp diffusion is proportional to what? Q times, it is the charge which is actually flowing. So the charge value got to substitute, that is you got to substitute Q. So here the Q is positive for holes. So Q times minus of dP by dx gives minus of Q dP by dx. So the minus symbol retains inside the diffusion current density for holes. So again we will be substituting diffusion constant to remove the proportionality, that is dP times q dP by dx. Minus of dP times q dP by dx is the formula for the diffusion current density due to the holes. So this is the formula for the holes, diffusion current density formula because of the holes, and it will retain the negative sign. So now we need to find out, so what is the total current density due to the electrons and due to the holes. So what is the total current density? It is drift current density plus diffusion current density. So just substitute here and we will get an equation which will be the total current density due to the electrons, that is drift current plus diffusion current. Similarly for holes we need to find out. So just add it, as Jp diffusion is negative, we will be getting here a negative symbol, and all other will remain same. So this is the equation for the total current density due to the holes. Now diffusion current, it's over. Lastly we will be studying one important relationship, that is called the Einstein relationship. Now what is Einstein relationship? Einstein relationship is between the diffusion constant, that is d, and the mobility mu. So both are the proportionality constant, which represents the ease with which the electrons or holes move inside the semiconductor. The only difference is here we are not giving any energy, external energy, and here we have to supply some external energy. They both will be related with the help of a voltage known as thermal voltage. So at room temperature, your thermal voltage represented as Vt is 25.9 millivolts. So here it is represented by a formula Kt by Q, where K is the Boltzmann constant and T is the room temperature, and the value of Vt at room temperature is 25.9 millivolts. So your Dn and μn are related with the help of Vt, that is Dn is equal to Vt times of μn, or Vt is equal to Dn by μn. Similarly your Dp is Vt times of μp, and your Vt is again it is dP by mu p. So we can get a common formula, that is Vt, which is equal to dN by mu n, which is equal to again dP by mu p. So this is a very important relationship which is called the Einstein relationship, which will be using in the next video, which will be for gate question semiconductor gate questions for semiconductor part 2. So that's it for this section, and stay tuned for my next video. Take care. Goodbye.